Talking about graphing polar coordinates and polar coordinates. And so first of all, we have a definition. Graph of a polar equation R equals f of theta consists of all points that have at least one polar representation R theta whose coordinates satisfy the equation. Okay, so easiest way to graph polar coordinates is first to kind of see this. We have a ray emanating from some origin, and think of us having circles that center about that origin with the same radius. In this case, the radius 1, radius 2, radius 3, radius 4. So suppose I wanted to plot, you know how we like plot x, y, where we go x distance, y distance, right? X distance, y distance. Here we're going to go r distance and then theta distance. So r is, how far this way we are. Suppose we wanted to graph the point, let's say 3 pi over 3, okay? Well, r is our radius, r, so we go to 3, and then we rotate this up pi over 3 and get a point right here. So this is 3 pi over 3, okay? Suppose we wanted a number like that's number 1, number 2, maybe we want, say, 2 comma pi over 2, so I'll go 2 pi over 2 gives me my point here, okay? That's kind of how we graph points, and we'll absolutely need this more when we talk about graphing polar coordinates. Suppose instead of graphing points, I give you an equation to graph, okay? Instead of graphing points, suppose I give you graph r equals 3, okay? Oops. Gee Louise. So if I want to graph r equals 3, then all I'm looking for is the set of all points such that the radius is 3. Now it doesn't matter what theta is. So r equals 3 will be the set of all points that have radius 3. So that will be this circle here, okay? So that's r equals 3. Suppose I wanted to say graph, that was number 1, here's number 2, graph theta equals pi over 6. Well, I want you to graph all points such that theta equals pi over 6. Well, theta equals pi over 6 will give me a line that goes here through that origin through there. Because this is pi over 6 this way. This has point 2 comma pi over 6. Right here it's 3 halves comma pi over 6. Right here it's 1 comma pi over 6. These are all the points in the world that have theta equal to pi over 6. All right, suppose we want to graph y equals 2 sine theta, right? So I've got theta, and just like creating a table of values, okay? I've got theta, and I've just put possible values for theta, okay? Now you can put any values, but those are the ones that I kind of put in. You could put 7 here, but we don't know sine of 7 necessarily, so we're kind of using some of those special values that we have, okay? And I'm plugging them in here to find out what is, just like if I plugged in x's and I was trying to find y's. Well, I got thetas, now I'm trying to find r's. So if I put in 0 here, I get sine of 0. Sine of 0 is 0. 2 times 0 is 0, correct? And then if I put in pi over 6, so sine of pi over 6, so again, 0, 0 is a point. Let me actually go back and plot that point. Okay, so 0, 0 is one of the points on my graph, right? So now if I plug in pi over 6, so sine of pi over 6 is 1/2. And if I multiply that by 2, I get the number 1, okay? So I have r is 1, and theta is pi over 6. So I go to 1, and I go to pi over 6, and I get my second point, okay? So pi over 6, distance at radius of 1, pi over 6, fantastic. Put my point right there. That's one of the points on my graph. Okay, good. If I put pi over 4, sine of pi over 4 is root 2 over 2. Multiplied by 2 gives me root 2, okay? So I'm going to put root 2 in here. So I go to root 2. Root 2 is 1 point change, right? And I go to pi over 4, and I get a little spot right there. Okay? Good. And then if I go to pi over 3, okay, pi over 3 is sine of pi over 3 is square root of 3 over 2 times 2. That just gives us the square root of 3, okay? So I'll have square root of 3, okay, which is not quite 2, and then pi over 3, which is up here, and it gives me another point right there, okay? And if I keep going here, if I put pi over 2 in, I'll get 2 pi over 3, square root of 3, square root of 2, 1, and 0. And if I plot these points, okay, at pi over 2, I have 2, so I go radius 2, pi over 2, awesome. And then I have square root of 3 again, good. And that's 2 pi over 3, right? And then I go 3 pi over 4, and it gives me square root of 2, good. Right there. And then I have 1 at 5 pi over 6. This is getting kind of funky a little bit, maybe a little bit better. There we go. And you see that this thing creates a figure like that, okay? And that, guys, right there is an interesting little figure. It's simply by graphing 2 sine theta, okay? Sometimes instead of plotting points, it's easier to graph a function by looking at it in an xy plane and then kind of converting it. So suppose I wanted to graph this in the xy plane. If I graph this in the xy plane, it's cosine theta amplified by 2 and then shifted up 2 units. And so it kind of looks like this, okay, in the interval 0 to 2 pi. And right here, pi over 2, and I know you guys can do this, 3 pi over 2, okay, as my point there, right there, okay, good. So if I want to graph this thing in polar coordinates, right, oops, graph this thing in polar coordinates, right, well, what happens? Well, as theta goes from, when theta equals 0, so I'm moving 0 this way, okay, my radius is 4. So 4 here, 1, 2, 3, 4. Got a point right here. Yes? All right, good. I've got all these imaginary little circles here. All right. But then as theta goes from 0 to pi over 2, right? 0 to pi over 2. The radius, okay, the distance here, okay, so if this is theta, this is r, the radius decreases from a height of 4 to 2. So I have a radius here of 4. And by the time I get to pi over 2, I should have only a radius of 2. So I want you to think about this. I want you to get from here and map it to here. So I'm gonna go ahead and, because eventually I gotta get to here, right? Because when r is 2, theta is pi over 2. But I got to think about like continuously getting from here and kind of moving around here. So I'm going to go like that. See how it's continually decreasing the radius? Okay. All right. And then as theta goes from pi over 2 to pi, my radius decreases from 2 to 0. Right now my radius is 0. So now from here to here, I got to get to 0 radius at pi over 2. So that's at pi over 2, I have a 0 radius. So from here, I've got to get to that spot like that. Okay. All right? Well, from pi to pi over 3 pi over 2, so now I've rotated from here to there, got that point. From there to there, I got this point. Okay? Now I'm going to go from here to there. Well, I got to increase my radius from 0 to 2. So I increase my radius as I wrap around this thing from here to here. I got to increase from 0 to 2. So I've got to wrap and get bigger and bigger and bigger. Good, as I go around. Awesome. And then here, as I go from 3 pi over 2 to 2 pi, my radius goes from a distance of 2 to a distance of 4. Okay, so that's just gonna, as I can't really do that. So if I go from here to there, I'll wrap it around. It's gonna look like that. Okay. All right. So this is an example of what we call a cardioid, because it looks like a heart. Like a cardioid, like a heart turned sideways. It looks like a heart. Okay. All right.